Our project is Improve EM, and our sponsor is our Professor Lei, and also one of our teaching assistant, Priya. We have 4 members in our team, and this is Alvin, and Junqi, and Kangbin, and Qinqian. So let's start with our overview of our presentation. There are 6 parts of our presentation, and I will start with the first one, description. Well, in the traditional EM algorithm, there are 2 main disadvantages. The first one is that running traditional EM algorithm is time-consuming for large data set, and the other is that given random initializations to traditional EM algorithm, it will lead to random performance, either good or bad. So in our project, we propose a new algorithm to improve EM, and our new algorithm should satisfy 2 conditions showing below. And the first one is to reduce the iteration number, and another is to increase the log likelihood. So next, my friend will talk about our project background.
There are many related work focused on improving EM algorithm. The first one is multiple random starting points, which overcomes the problem of local optimal. But this algorithm increases the computational quantity tremendously. The second one is engineered EM, which combines genetic algorithm. It's designed a new schedule to terminate bad EM run and improve the multiple start points strategy significantly. The third one is partial step. Because in EM algorithm, step consumes most computing resource, and some works has focused on optimizing this part, especially for large data sets. Lazy EM is one kind of such algorithms. It identifies which part of data set is significant to the change of Q function in each step, and only use this subset to update Q function in each iterations. GPU, Hadoop, and MapReduce are using new technologies, things like parallel computing, faster processor to accelerate EM algorithm. Inspiring by the ALEM, we are interested at the distribution of likelihood and iteration numbers from different initializations. So we have done many experiments to get these results. Both figures are part of our experimental results, and after we did, and from our previous work before the last presentation, after we did this, we found some interesting patterns and arose several new ideas. The first one is that we can use specific initialization instead of random one. The second is we can fix part of the initialization parameters which is associated with the observed data, and only updates the rest of parameters through the EM run. The third one is in large data case, we can sampling a subset from the whole data set and use this subset to learn an intermediary factor graph, which is the parameter, and use this intermediary factor graph as the initialized factor graph to learn the whole data set. Since time is limited, we just focus on our last idea. Intuitively, samples have similar distributions with whole data sets. So what we have done in subset EM is that first we initialize the factor graph randomly, and we use this factor graph to learn a subset of our data sets and produce intermediary factor graph. and use this intermediary factor graph as the initialized factor graph to learn the whole data set. What we need to verify in this method is not whether this method can improve the likelihood and computing speed at the same time, and what sample size should we choose to optimize the result, the successful rate. So we have designed sets of experiments to figure these problems out, and now let's Junxi introduce that to you.
Yes, thanks. To investigate the feasibility of our proposed algorithm, and if so, to find how three factors, namely initializations, number of hidden variables, and the sample size, affect our algorithm, we designed 3 sets of experiments on the alarm dataset with size 4,000. This dataset has 31 hidden variables, 31 nodes. In the first experiment, we fixed the number of hidden variables and sample size to 7 and 100 respectively, and we have used 100 different initializations. And in the second one, we look how the number of hidden variables affect the algorithm, and we use from 1 to 30 and fix the sample size at 100. And we use 3 different initializations to avoid the randomness, which may lead to unexpected state. And in the last experiment, we use sample size from 50 up to 3,800, and the number of hidden variables is fixed at 7. Also, 3 different initializations are used, and in each experiment, for each set of parameters, we have samples for 15 times, and we will look how many times using SEM will be successful out of the 15. And then Alvin would like to show the results of these 3 experiments.
Okay, here are the results of our experiments. This is a figure showing the results of the first experiment. In this experiment, we randomly choose 100 initialization points and run them for several times to get the result. Here, x-axis represents the initial log likelihood, and the y-axis represents the successful rate. Previously, my friend Qing Qian has already defined the definition of success, which means that the time is less than the original one, and the log likelihood is better than the original one. So what we can see from this figure is that when the initial log likelihood is neither too good or too bad, SEM will get a good result. So here is the result for the second kind of experiment, and the x-axis represents the number of hidden variables, and the y-axis is also the successful rate. What you can see from this figure is that when the number of hidden variables is neither too small or too large, SEM will work. And we did this experiment for several times, and we have 2 other figures to show this result. And here is the second one, and here is the third one. So we can draw the same conclusion from these 3 figures. And here is the result for the third kind of experiment. The x-axis represents the number of sampling sets, and the y-axis represents the successful rate. We can see from this figure that when the sampling set is very small, SEM will not perform well. It is mainly because that when the data set is very small, the distribution of the smaller data set is not very close to the real distribution, so SEM will perform badly. And when the sampling set is very large, then SEM will not make any sense, because it takes some time for SEM to do sampling, and it also takes SEM to verify the data set. So when the number of sample sets is very large, the time used for us to run SEM will exceed the original ones. So here is the one run over SEM, we can see from this figure that the blue line represents the original EM and the red curve represents the SEM. And we can see from this figure that there's a blank region ahead of the red line, which represents the time used to do sampling and to evaluate the sub data set. And we can see from this figure that SEM used less time than the original EM, and although we may not see clearly from this figure, but the log likelihood increased a little bit than the original EM. So here are the conclusions we got from our experiment. When the initial log likelihood is neither too good or too bad, SEM will work, and the number of hidden variables really matters during this process. For example, we have only 31 nodes in this this Bayes network, and we cannot have the number of hidden variables too large or too small. Then the SEM will work, and also sampling size affects the result also, because when the sampling size is too large or too small, SEM will fail for the reason I have explained previously. So these are all the experiments we did. Thank you.
Very good, thanks. I had one question. Let's take that. If you could go back a few slides, if you don't mind, to the this one right there. That one I found interesting. Obviously here, I think on the y-axis you have some measure of the quality or the success.
Successful rate.
Yes.
The successful, okay. So obviously the success is better here in the sort of the mid-range, from 1,000 maybe up to 2,005 or something like that, or 1,000 to up to 2,000. I was wondering what is the execution time here or run time? Is it the same across the board here from 0 and up to 3,700, or does also the execution time vary with the success here as well? Are you keeping the execution time constant, or does it vary?
What do you mean by execution time?
So I guess for it looks like you have several experiments here, and so this is some measure of the quality of the result of the experiment. And I guess each experiment also took some time, right? You ran the EM algorithm. How long does each run of the EM algorithm take for each of these cases? Did you run it for an hour and then you stopped it, or did you run it for a varying amount of time?
We run this algorithm until it converges.
Oh, okay. Yeah. So then I guess the other interesting question here is what is that? How long? What was that convergence time? Was it 30 minutes? Was it 5 minutes? Was it now 60 minutes?
In this figure, we haven't included that, but the convergence time using SEM is shorter than using baseline EM.
Okay, good. That's good news.
We have data, but we haven't included in this
Right.
figure.
Yeah. So that's going to be important information to include in the report, for instance.
For sure.
Okay. Very good. Any more questions about that? In the meantime, let's make sure the deep learning team starts walking towards the podium. Any questions from Pittsburgh about the Improve EM team's presentation? Okay, in that case, let's thank the speakers.
Thank you.
Thank you.